Yeah, the next topic is grand plot to find the end point. Yeah, there is a, very different way to find the end point. In this case, you don't need to do the um, what to get the entire titration curve, but you get several points before the equivalence point, and then from those points you can uh, you can obtain the end point. Okay, that is called grand plot. And grand plot is the way of finding end point using data from before end point. Yeah, that's very important. Before end point. If you take the data after end point or at the end point, nothing works. Okay? Typically, 0.8 equivalence point or zero point 0.9. Okay, yeah, that's very important. The principle is quite simple actually. Let's take a look at this equi equilibrium constant for weak acid. Okay, here we wrote this activity coefficient. Okay, why? Because pH electrode respond to activity. Okay, so for the sake of more accuracy, we included this activity coefficient, gamma values for each species. Okay, consider titration of weak acid, HA, and this is FA and VA is the weak acid um, initial. Yeah, actually, this is the formal concentration and volume. Okay, and to the solution of weak acid, we add strong base, whose concentration, formal concentration is Fb, and volume is Vb. Vb is variable. Okay, it changes. Now here, from this equation, we write for A minus. Okay, this is the ratio of mole of OH minus delivered divided by total volume. Okay, it can be expressed by this one, and remaining HA concentration is what? The denominator is the same, but numerator is the initial moles of HA minus added moles of base. Okay, yeah. And Ka, this one is can be rewritten as this equation, and by rearranging this equation, we get a rather complicated this equation. Okay, here the left hand side, we see the VB, added strong base volume and proton concentration, which is 10 to minus pH, and right hand side, this one. And look at that here, the this first one, this term VA uh, multiplied by FA divided by FB, that is what? Equivalence volume. Okay, that's the equivalence point, VE. So this equation can be simplified to this one, VB times 10 to minus pH equals gamma ratios, and this one Ka, which is the equilibrium constant, and multiplied by VE minus VB. Okay, this pH is easily obtained using pH meter. Okay, yeah, and this part, left hand side, this is Y. Okay, and then on the right hand side, only variable is VB. Yeah, that's the X value. Okay, others are constant. Okay, so current plot is plot of VB times 10 to minus pH versus added base volume. Okay, this one. So here, this is a simple linear equation. Okay, linear equation. Although complicated looking, this is a linear equation, and this one. What is um, the slope? Slope is a negative of this one. This gamma ratio multiplied by Ka. Yeah, that's the uh, what the slope, and y-intercept is this one, this part. Okay, so here when VB equals VE, okay, the right hand side is 0. Okay, yeah, So, but you need to take data before the equivalence point. Okay, here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, but you although you took uh, 10 the data points, yeah, and as the volume approaches this equivalence point, this one is what the points deviate from this linear. Okay, so you took only linear points. Okay, those points on the linear line. Okay, and here you take you ignore last the 4 points. You take only the first 1 2 3 4 5 6 points, and then draw the straight line, and then you read notice x intercept. That's the equivalence point. Okay, that's the volume at the equivalence point. Okay, and from the slope, yeah, you can calculate this equilibrium constant. So from this grand plot, mm, we can get both this equivalence point and what this one equilibrium constant. Okay, very convenient. But but remember, yeah, you take data before the equivalence point. But it is good practice. You take the many data points, and then find out which data points are on the straight line. Okay, and take those data points only. Yeah, others are ignored. Right. Yeah, this is why these data points are deviated from this straight line. The source of curvature is when VB approaches VE, the approximation that every moles of hydroxide ion generate 1 mole anion is not true anymore. Okay. Also, the change in ionic strength, this one, these okay ratio varies as strong acid is added. Okay, this variation can be avoided by maintaining nearly constant ionic strength. Okay, to minimize this change in ionic strength, we add neutral, yeah, not interfering species like sodium nitrate. Okay. Okay. Next topic is finding the endpoint with a pH indicators. Okay. This is a very traditional way to find endpoint because there are many organic species whose colors depend on the pH. Okay, for example, this Timor blue. This is a rather complicated organic species. It is weak acid. Okay, it contains this hydroxyl group. Okay, and there are two proton species that are dissociated. Okay, and this one it dissociates stepwise. Okay, the first dissociation, the pK1 is 1.37, and second dissociation is pK2 is 8.9. But what is nice is that depending on the dissociation, there are three species and colors are all different. Okay, that's quite amazing. Right? Simply proton addition or removing the proton, okay, makes those species color all different. Okay, the fully protonated form takes red color, and this only one proton dissociated, the color yellow, and then fully dissociated form takes blue color. Okay, so since it is a weak acid, we can write this dissociation equation, and then we can define we can write this Henderson Hassel-Paley equation. pH equals pK1 plus log the ratio of, for example, for these two species, the ratio of the yellow form and the red form here. So what can you learn when this red form is concentration is more than 10 times of this yellow form? Okay, and what is the pH then? This is what? This is 10 at 1 log 0.1 is -1, so pH equals pK1 minus 1. Okay, that is the pH 0.7. Okay, in this case, the color is dominated by this red one. Okay, the red color. Solution takes the red color. Okay, so now we can. That's the rule of thumb. If the solution pH is 1.7 or less, and then solution color is dominated by this one, Timor blue. This red one. Okay. And what about the the Y form is 10 times or higher or more, okay, higher than this one. That pH is what? This log 10 is 1, okay. pH is 1.7 plus 1 is 2.7, okay. So from pH 2.7 and up, the color is dominated by this one, yellow one, okay, in yellow. And but what is in the middle? Middle pH between 0.7 and 2.7. The color is there is a mixture color. Okay, this is orange, red and yellow. Mixed color is orange. But if pH is close to 0.7, the color is what? Red like orange. Okay, or orange like red. And if pH close to 2.7, the color is orange like yellow or yellow like orange. Okay, yeah. So rule of thumb is that what? This rule says that if the concentration change ratio is more than 10 times, then the color is dominated by the more abundant species. Yeah? That's the rule of thumb in this case. Okay, here is another example. This is the very commonly used indicator, phenolphthalein. Okay, this phenolphthalein, yeah, at alkaline solution, the color is what? Color is red, but in acidic solution, color is no color, colorless. Okay, here. So this is a good indicator for the titration of a weak acid with strong base. Okay, this one. So look at that. Uh, this one is fully protonated. Okay, the color, there is no color, colorless. Okay, and below pH 8, but when pH is above 8, this fully dissociated form, the color is pink. Okay, but what about the in a strong acid? Okay, like in sulfuric acid. Hmm? This part, let me see. Yeah, this part is also protonated, and then it takes orange red color. But this is what this is exception. Okay, because we don't have many cases working in this very strong acid. Okay, but in very strong base. Okay, more than pH more than 11, and then the species lose color. It becomes colorless. Okay, yeah, but this is also exception. Yeah, there are not many cases we are working at this very high pH. Okay, and indicator error is the difference between the observed endpoint and true equivalence point. Yeah, that's the indicator error. You see, indicator error is somehow unavoidable, but we have to make to minimize this indicator error. Okay, yeah. So it is very important to select a proper indicator. Okay, there are many indicator molecules. Okay, you will see soon. And in this case, look at this figure. Here, this around here, this is the equivalence point, and which indicator should we use? Okay, let's consider the two indicators. The first one is this one, bromocrasol green, and another one is bromocrasol purple. Okay, the bromocrasol green in this case, its color changes. You see, around pH 5.54. Okay, and it takes a blue color. Okay, from a pH around 5.5, okay, blue color. And then when pH is lower than this one, 5.5, and then it becomes it turns color to yellow. All right. But in the meantime, bromo gradual purple. Okay, the color, the in acid solution color is yellow, and it changes color to purple. Okay, but pH range is what, from 4 point something and from 6 point something. Okay, here. Okay. So which indicator should be used? Okay, and well, maybe this one. This bromo gradual purple is the adequate indicator. Now, because since this titration curve is the titration of weak base with strong acid, okay, so the equivalence point appears in the acidic region, around pH 5.5, okay, here. And when we use this bromo gradual purple, and then we titrate with strong acid, and then we may stop, you know when the color is the mixture color of purple and yellow. What's the color? When purple and the yellow is they are mixed color, the red will be intermediate color. Okay, yeah. So it is rather easy to find the end point with this bromo gradual purple. But what about the with the bromo gradual green? Okay, so we have to stop after the solution takes quite a strong blue color here. Okay, but determine how blue, yeah, hmm? At which blue uh, to stop. It is not very certain. Okay, yeah. So the choosing indicate proper indicator is very important to avoid to minimize indicator error. Okay, this list, yeah, there are the long list of common indicators depending on pH transition here. Okay, for example, methyl violet. The transition color is what? Transition pH is quite strong acid. Yeah, okay, yeah, and gradual red. Okay, it also uh, undergoes color change at very acidic solution. Okay, I like that. Okay, so looking this table, we can choose a proper indicator. Okay, for our purpose. Okay, the next topic is a rather peculiar one. Okay, that is called Hammett acidity function. Yeah, symbol is H0. Okay, H0. Yeah, Hammett acidity function. And Christian, Hammett and his students asked a question: how do we measure acidity of a strong acid and super acid? Okay, there are very very strong acid, and there are acids, so-called super acid. Okay, in that case, how do we measure acidity? For example, you look at that. This sulfuric acid, okay, 100% is quite a strong acid, and if you blow this one sulfur trioxide, this is gas, into the sulfuric acid, this acidity of sulfuric acid becomes even stronger. Okay, or this one, fluorosulfuric acid, or this one, fluorosulfuric acid and 10% what antimony hexafluoride. This is called the superacid. Yeah, like that. Those species, yeah, acidity is too strong. So in ordinary way, we cannot measure the acidity. Yeah. So the Hamet asked this question: how to measure the acidity of strong acid or superacid? Okay. Yeah. So he invented his own way. The idea is that what, this is a so strong acid, so the acidity is so strong. so they can react with a very weak base. Okay, so measuring this acidity based on the very weak base. Okay, here look at that. This is a B. B is very weak base. So this B is so weak. Okay, this B is so weak so that the when dissolved in water, since the persistence is so weak, it cannot take any proton from water. Why? Because the persistence. This is so weak base, but although it is very weak base, it can react with very strong acid, like these acid. Okay, and then these acids listed here are so strong, so it can protonate. This is a very weak base, so we can write this kind of what this Henderson-Hasselbalch like equation for the this weak base. Okay, yeah. But here we instead of write using the pH, but we use H0. This is Hammett function. Okay, H0. H0 form is the same as the Hammett Henderson-Hasselbalch equation. H0 equals pKa, but here pKa is what? For pH plus in a conjugate acid of very weak base. You see this one pH plus. Since B is a too weak base, so its conjugate acid pH plus is what? This pKa value is very small. It has a negative value, even negative values. Okay, you understand, right? So B is very weak base, and its conjugate base in this case is a very strong acid. Okay, here, right? And uh, here it is given by this equation, and then uh, by measuring B concentration of B and pH plus by other means. Okay, by other means, we can calculate the H0, okay, which is the acidity for a strong acid. Okay, yeah. The idea here is that um, since these acids are so strong, okay, so ordinarily by the ordinary way, it is not possible to measure the acidity. Okay, so Hammett invented a kind of new way to use weak base. Okay, very weak base. Okay? But here is a some similarity to pH. For the dilute aqueous solution, dilute. If the solution is more and more diluted, H0 approaches pH. Look at this figure. This x-axis is mole fraction of acid, and y-axis axis is Hammett constant, Hammett function H0. Okay, so this mole fraction of acid, becomes smaller and smaller. When it approaches zero, that means what? Dilute solution, and then this one, this H0 value approaches pH. Okay, but question problem is when the mole fraction is becomes greater and greater. Yeah, that means for the very concentrated solution, right? So then ordinary pH measurement is not possible. So in this case, we use Hammett constant. All right. Yeah. Negative pH usually means H0. Okay. Sometimes you see, you may find that this solution pH is minus more 10, minus 11. And then you may think, how it possible to have such a negative pH values? But don't be confused. That pH usually means H0 here, okay? H0. So for that, 100% sulfuric acid, H0 is minus 11.93, and like that. And then even this one, fluorosulfuric acid plus 7% antimony hexafluoride and fuming. This one, uh, fumed, adding this sulfur trioxide. In this case, I don't know the name is not given here, but that for that base H0 is minus 19, 0.35. Okay, okay, look at that. This figure shows the depending on mole fraction of acid, H0 value, varies. Okay, yeah. This is a very special case for the very strong acid and super acid. Okay, this one is called super acid. Okay, here is the practical notes. Okay, we often use this strong base, sodium hydroxide and the potassium hydroxide, but problem is that their concentration uh, uh, is not very precise. In other words, these species, they are white solid, they are not primary standard because containing carbonate. Okay, they contain a lot of carbonates. Uh, we have to you have to standardize with primary standard of acid. Okay, and then usually potassium hydrogen phthaleate. Yeah? This is a weak acid, but it can be used as primary standard. All right. So this alkaline solution must be protected from air, otherwise they absorb CO2. From the alkalinity section, I showed you, in alkaline solution, CO2 solubility is much higher than in a neutral or acidic solution. Okay, this why? This hydroxide ion reacts with this one CO2 to make this one bicarbonate. Okay, so uh, when you prepare this alkaline solution, and then you have to prevent the 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 CO2 in air from entering your solution. Okay, yeah. So if not, otherwise the concentration will be changed. Okay, by introduction the CO2, the solution pH solution becomes more and more acidic. Okay, usually we use polyethylene bottle to contain alkaline solution, because don't never contain this basic solution, alkaline solution, in glass bottle, because this hydroxide ion now etches the silica, okay, SiO2. So never what uh, put your alkaline solution in a glass bottle, okay, but in a polyethylene bottle. Okay, and boiling this alkaline solution in a flask for 1 hour decreases the molarity by 10%. Why? Because boiling means the removing the dissolved CO2, so molarity changes. Okay, that's the practical notes. Okay, here are this primary standards. Yeah, primary standard is that they are very pure compounds. Yeah, very pure, and the molecular weight is rather on high. So to minimize the weighing error, and they're very stable, pure, stable. Okay, yeah. So those compounds could be used as a primary standard. Okay, using this acid or base primary standard, you can standardize this basic solution or acidic solution. Okay, by ordinary means. Okay, next topic is Kjeldahl nitrogen analysis. Okay, this one people pronounce Kjeldahl. Okay, Kjeldahl. Nitrogen analysis is very important, especially in food science. Okay, food scientists all the time analyze nitrogen content in food. Yeah, because for example, the proteins. Proteins is the composed of amino acid, and each amino acid contains nitrogen, because it contains amine group, right? So by analysis of nitrogen contents, so we can estimate, oh, this food contains this percentage of protein. Okay, so most proteins, the nitrogen content is about 16%. Okay, and how do we analyze nitrogen in food or in anything? Yeah? First, usually food contains only these three, mostly these three elements: carbon, hydrogen, nitrogen. And when you boil this compound in a very strong acid like sulfuric acid, and all the molecules are decomposed, and nitrogen becomes ammonium ion because it is a very strong acid, and carbon decomposes to carbon dioxide, and hydrogen becomes water. Okay, and then you, after the this is called digestion, right? And then you neutralize this solution, and CO2 is already removed, and then this one neutralize means what? You add hydroxide ion. This ammonium ion reacts with hydroxide ion and becomes, since the pH is increased to to basic, then this ammonium ion becomes ammonia gas. Okay, ammonia gas. So ammonia gas what is is distilled from this solution, yeah, and then it reacts with strong acid. Okay, this one of known amount. That is important. Yeah. So now distilled ammonia gas reacts with known amount of strong acid HCl, so it becomes ammonium ion again. And then there are, so since you added excess of hydrochloric acid, there are excess protons. Okay, and then unreacted proton is titrated with sodium hydroxide. Okay, yeah, this series of reaction is very efficient to analyze nitrogen, in especially in food. Okay, and they are all acid base chemistry. Okay, so the acid base chemistry could be used, yeah, practically, yeah, to analyze nitrogen, and especially in food. Okay, this figure is the original apparatus, okay, used by Dutch chemist Kjeldahl. And next topic is the leveling effect. What is the leveling effect? Okay, we are working usually in aqueous solution. Yeah, the aqueous solution. Yeah, since you are mostly working in aqueous solution, and then these strong acid, the perchloric acid and hydrochloric acid, they are all strong, very strong. So it is difficult to differentiate which one is more much the stronger. Okay, but if we use other solvent than the water, then this acidity could be differentiated, like in acetic acid, this perchloric acid and this hydrochloric acid react with acetic acid. In this case, this acetic acid is a solvent. Okay, and then for perchloric acid, K equilibrium constant is 1.3 times 10 to the minus 5. Oh, suddenly this perchloric acid becomes weak acid in this acetic acid solvent. Okay, what about HCl? Wow, K is even smaller. Okay, 2.8 times 10 to the minus 9. Okay, so in acetic acid, perchloric acid is more the much stronger acid than hydrochloric acid. Okay, and here the leveling effect is what? Level means what? You make it flat, right? So the acidity, yeah, the difference cannot be determined. Yeah, that's the leveling effect in water. Okay, they are all strong acid. Yeah? So they are leveled. Okay, the acidity is leveled. Okay, leveled off. Yeah, here. Uh, this shows that in I think the the mixture of methyl isobutyl ketone, okay, and then uh, you have several 1, 2, 3, 4, 5 different species, and they are titrated, yeah, and then y-axis in this case is potential, okay, because they maybe virtually the protons are not many, yeah. So first the perchloric acid is titrated, and then hydrochloric acid, and then 2-hydroxybenzoic acid, acetic acid, and hydroxybenzene. So in this case, in this solvent, okay, the which one is the strongest acid? Perchloric acid, then hydrochloric, and then like that, okay. They are all differentiated, okay, in this special solvent, okay, yeah. Okay, like that. Mm, Here, let's consider a base such as urea, okay, whose Kb is 1.3 times 10 to minus 14. So urea is a very weak base, okay, and titration with perchloric acid in water, this one, okay, is protonated by this strong acid, okay. But that's too weak to give a distinct endpoint, yeah? Because K4, this equation, is very not large enough. Yeah? If S is stronger than this uh, this strong acid or available, titration reaction might have an equilibrium constant large enough to give distinct pH endpoint. Okay, yeah. Here is the example in charge of water to acetic acid. In change of water to acetic acid, okay? By changing to acetic acid, hydrochloric acid must much stronger acid than this one, uh, this proton in acetic acid, okay? So uh, in acetic acid, this base could be titrated with this hydrochloric acid, okay. So we can have clear endpoint, okay. So there is no more discussion. And the point here is that when titration is not easy in aqueous solution, the changing the solvent may give us a clear endpoint. Yeah, that's the point. Okay, but usually, the kind of practice is not usually done. Okay, next topic is calculating titration curves with a spreadsheet. Okay, this is a very practical thing. Yeah? So I strongly recommend you read this section carefully, and then yeah, without titration we can construct entire titration curve. Okay, and I have to show actually with Excel, but mm, I cannot do it here. So I strongly recommend you to read this section very carefully, and then have full knowledge of how to do it. Okay. The first example is the titrating a weak acid with a strong base. Okay. Titration of VA, volume of HA, whose concentration is Ca, with VB of NaOH, whose concentration is Cb. Okay. First, you write the charge balance equation. Then sodium ion concentration is given by this equation, and this formal concentration is sum of HA and plus A minus N given by this equation. And then here a minus is alpha is the fraction, okay, uh, multiplied by formal concentration. Alpha is given by this one, you already know that. And then this charge balance equation can be rewritten uh, here. Let me see, and let me see. Here proton, and instead of sodium concentration, we use this one, and instead of anion the concentration, we use this equation, and for hydroxide ion, yeah, here. And then rearranging that equation, finally we reach this one, okay. This is phi. Phi is the fraction of a titration for weak acid by strong base, okay. This one is given by this one. And then the right hand side is rather complicated, okay. Now here is an idea how to construct the entire titration curve. Is that, you see, in ordinary titration we add strong base, yeah. We plot the pH versus added the base volume, okay. But in this simulation we do the different way. Mm. We first we list proton concentration. In other words, we uh, you know gives pH, yeah, from low value to higher value, okay. And then we find out the added the base volume, okay. You understand the procedure in simulation? The procedure is the exact opposite. First you determine the pH, yeah? And then we calculate using this equation and this one, okay, the base volume, all right. Yeah. Now this one, this example is the titrating weak acid with weak base. This is not a usual practice, but anyway, theoretically it is possible to titrate a weak acid with weak base. Okay, and then this equation for phi is similar, well, a little bit different here. Okay, in this case again, we first determine the pH, and then we find out this base volume. Okay, like that. And this is a very general case of titrating a weak acid, triprotic acid with a weak base. In this case, this one dissociate in 3 steps. Okay, phi is given by this one, and then I recommend you to drive drive this equation. Not this equation. It's not easy to drive, but if you look at the textbook, you may have idea on how to drive this equation. Okay, this one is rather complicated, but that's okay. 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 Yeah, this is end of chapter 10. I selected these problems, and then you solve, and then you scan or you take a photo and upload. Okay. Right. When I have a time, I will show you how to simulate titration curve, and then from the spreadsheet we could very clearly see the titration curve change depending on what this equilibrium constant. Okay.